Hi students, here is Sushri Priyadarshini, lecturer in Mechanical Engineering from Bose Cutter. So, in this class, we will continue with the remaining part of the air compressor, that is the derivation of work done for the multi-staging air compressor, and also we will continue with the free air delivery. In the previous class, I have taught you about the volumetric efficiency, and also I have derived the expression of work done for single acting air compressor with clearance and without clearance. So, today we will continue with multi-stage air compressor, and also we will study about the free air delivery. This is our content, and also I have completed almost all the parts, and also in this class we will solve simple problems, and I will derive the work done for two stage compressor with and without clearance. Okay. So, let us start from the free air delivery. Okay. In the previous class, I have completed the about the volumetric efficiency, free air delivery. In the first class, I told you about the free air. In the terminology part, I told you about the free air delivery. That means FAD. This is most important, and you need to understand what is free air delivery. Okay. Actually, what happens after the compression process, we are storing the compressed air in the storage tank, which is at higher pressure, which is our required pressure or higher pressure, that is might be P2, that is might be 10 bar or 20 bar. This depends upon our requirement. But what happens when that volume of air is expanded up to the atmospheric pressure? When it will be allowed to expand, that will be the pressure will be reduced to atmospheric pressure and temperature condition. Okay. And if you will calculate, or if you will store that expanded volume, if you will store in a cylinder, in a different separate cylinder, and that volume is called as free air delivery volume. Okay. And that volume corresponds to atmospheric condition. That means the volume of the compressed air corresponding to atmospheric condition is known as free air delivery. And why we are studying about the free air delivery? Because initially the amount of air entering into the cylinder, that is our actual. Okay. But it is all what the piston displacement volume, that is our, that amount of air should enter into the cylinder. Clear? That piston displacement volume, that is called as swept volume. But actually that amount of air is not entering into the cylinder because of different reasons. Previously I have told you there are several reasons that amount of air is not entering into the cylinder, because sometimes clearance volume is there, the expansion of clearance volume happens, and also the cylinder temperature, wall temperature is higher. Due to the higher temperature, when fresh air is entering inside the cylinder, and when it is coming in contact with the high temperature cylinder, that also again the specific volume of that air increases, and that reduces the effective stroke volume. That might be the reason. And also sometimes the obstruction of inlet valve, that might be the reason. So, due to some reasons, these three are possible reasons. So, due to some reasons, the actually air that should enter into the cylinder, that is not entering into the cylinder. Okay. So, that is why we are calculating the compressed air volume by allowing it to expand at atmospheric condition, and we are storing in another cylinder, and we are calculating the what is the volume of this cylinder when this air when it expands up to the atmospheric condition, and that volume is called as free air delivery, and it is measured. It is noticed that the free air delivery volume is less than the volume which is actually entering should enter into the cylinder. That means the volume which is corresponds to initial atmospheric condition, swept volume, that the FAD is less than that of that volume. So, it is the volume of compressed air measured in meter cube per minute reduced to atmospheric pressure and temperature, because it was at higher temperature and pressure after the compression. When it is reduced to atmospheric temperature and pressure, that is measured in meter cube per minute. What is this value? And that value is called as free air delivery. And what is the formula of free air delivery. Actually, we have to apply the law, that is we have to take two conditions, one is atmospheric condition and what is another is suction condition. So, atmospheric condition we will take the point F, Pf, Bf, that is divided by Tf, that is equal to suction condition, that is P1. Okay, you all know the suction happens at pressure P1, and what is the volume P1, B1 divided by B4, that is effective stroke volume, that divided by B1 T1. Okay. So, Bf is equal to P1 into P1 minus P4 divided by Pf and divided by T1, that is equal to P1 divided by Pf T1 into B1 minus B4. This is the value of what? Volume of free air delivery. It is measured in meter cube per minute. This corresponding to this value is corresponding to atmospheric condition when it is allowed to expand up to atmospheric pressure and temperature, and Pf is the atmospheric pressure and Tf is the temperature, atmospheric temperature when it is reduced, and Vf is the free air delivery. This is the FAD, free air delivery. And what is this P1 T1? P1 is the suction pressure, suction temperature, and B1 and B1 minus B4 is amount of air entering into the cylinder. Clear? So, this is the condition, this is the derivation of free air delivery value. You can also solve the problem if question is given like calculate the free air delivery value, and you can relate this conditions, atmospheric condition and suction condition, and you can find out the value of free air delivery. So, this is all about your free air delivery. After that, we will continue with multi-staging air compressor. Okay. And here we will derive the work done for two-stage air compressor. And also about the multi-staging, I have already discussed in the first class what is the difference between the single stage and multi-stage, and why the multi-stage is given. When the pressure is very high and we cannot compress the air in a single stage, at that time we will use two cylinders to compress the air up to very high pressure, and that is called as multi-staging air compressor. And here the diagram, the PV diagram is for two cylinder air compressor. One is low pressure cylinder and another is high pressure cylinder, and in between the low pressure cylinder and high pressure cylinder one intercooler is there. Okay, I have told you already, again I am telling, this is the suppose low pressure cylinder and this is the high pressure cylinder, and in between those cylinders one intercooler is there. And what is this function of intercooler? Intercooler reduces the temperature which is coming out of the low pressure cylinder. That means the air is entering into the first cylinder at atmospheric pressure and temperature, but when the delivery of air takes place, the temperature increases, because in the compression process the temperature, pressure as well as temperature increases. So, our requirement is the higher pressure, our requirement is not the high temperature air. That is none of our business. So, that is why we have to reduce the temperature up to the initial temperature at which air has entered into the cylinder, and if the air the temperature will be reduced exactly up to the initial temperature, then that is called as perfect intercooling, and that is a function of intercooler. The aim of the intercooler is to reduce the temperature of air by putting constant the pressure. Okay, at constant pressure it will reduce the temperature of air. Okay, so that is why here what we will do, in the intercooler temperature drops. Okay, and I told you that if the temperature will be reduced up to initial temperature exactly, then that is called as perfect intercooling. If that is not done, some temperature difference is there, then that is called as imperfect intercooling. Okay, only difference is that. And after that this is the P2 and temperature suppose T1, perfect intercooling happens. This is P1 and T1. This air will enter into the second cylinder. Okay, in the second cylinder the pressure obviously the compression happens, and after the compression pressure increases and also temperature increases, and when it will be delivered the pressure will be P3 and temperature will be suppose T2. Clear? And this pressure is the higher pressure. If intercooling is not done, then high temperature air will enter into the second cylinder, and that requires more amount of work input for the compressor. Okay, so if we will do the intercooling process, the amount of work done which we have to provide to the compressor, that will be reduced. That we will understand by doing this work done derivation. Clear? So this P3 is requirement, our requirement, this air will enter into the what? Storage tank. Okay, definitely this is very high pressure. That's why we are doing in multi-staging. We are not doing it in a single stage. We are using the multi-stage air compressor. Okay, and now we'll derive the formula of work done for the two-stage air compression. Here you can see there are two cylinders, one is low pressure cylinder and another is high pressure cylinder. Okay, and here AB process is the what? Compression process, and CD process, C2D process is another compression process in the higher cylinder, and here G2H is the expansion process in the low pressure cylinder, and E2F is the expansion process in the higher cylinder, high pressure cylinder. Okay, and what we have to do? We have to do in two phases. First, we have to find out the individual work done for low pressure and high pressure cylinder, because net work will be work for low pressure cylinder plus work done for high pressure cylinder. We have to add this amount of work. Okay, and previously here clearance has been provided. Previously we have studied about the work done for the single stage air compressor with clearance. Clear? So if I will calculate the work done for low pressure cylinder, then what will be the formula? N by N minus 1 P1 into VA minus VH. Okay, VA minus VH whole into P2 by P1 to the power N minus 1 by N minus 1. Okay, so this is the formula for work done for low pressure cylinder. If I am calculating the high pressure cylinder, then N by N minus 1 P1 into VC minus VF, this amount of work, VC minus VF. Okay, whole into P3 divided by P2 to the power N minus 1 by N minus 1. Okay. So now we will find out the net work. W net is equal to low pressure plus W